So hello, I'm Dr. Hannah Menke, and I'll be talking to you about our four-dimensional imaging method of pore-scale reactive transport in carbonates and a few of our results. Storing carbon in oil reservoirs has the added benefit of mobilizing more oil for extraction while mitigating climate change. In fact, over 50% of world oil is stored in carbonate reservoirs. Now, as you all know, when CO2 is mixed with water, it becomes carbonic acid, and when acid comes into contact with carbonate, it can dissolve the surrounding pore structure by a measurable amount. This dissolution can, in turn, increase the number and size of permeable pathways for oil to be extracted from the reservoir and significantly affects CO2 storage capacity and permanence. However, all dissolution is not created equal, and is in fact condition dependent. When and how this dissolution happens directly dictates how fluid flow changes in the porous media. And these changes must be fully understood if we hope to upscale from the pore scale to the reservoir scale and make accurate predictions of flow and transport. The way we visualize the flow properties is with the Dom-Kohler-Peclet space. The x-axis is flow rate represented by the Peclet number, and the y-axis is reaction rate, or Dom-Kohler number, which must then be multiplied by the Peclet number in order to isolate reaction from advection and make the axes independent. When the flow rate is very high, dissolution is advection dominated, and we see uniform dissolution. When the flow rate is low and the reaction is high, the dissolution is diffusion dominated, and we see the front of the rock dissolve. This is called compact or face dissolution. With both flow and reaction rates high, the dissolution is dominated by preferential flow paths, and we see wormhole formation. The placement and slope of these boundary lines are dependent on the intrinsic rock properties, be that composition, permeability, heterogeneity, etc. We designed this experiment to simulate CO2 saturated brine in very close to the wellbore at around 1 kilometer in aquifer depth. The flow rate was relatively fast to encourage fully mixed fluids in the pore space, and we used the highest reaction rate possible under these high temperature and pressure conditions by equilibrating our brine with CO2 at 50 degrees centigrade and 100 bar with no added buffers, which works out to be a pH of 3.1. We then pumped this fluid through the rock for 2.5 hours and took 10 images during reaction. We chose this Qatar limestone for this benchmark study because it has a homogeneous pore structure that is well connected with large grains and pores that are easy to resolve within the limitations of our microscope. Additionally, it is chemically homogeneous, being 97% calcite and the remaining fraction being quartz. So here is our core next to a British penny, which for all you Americans out there is about the same size as an American penny. It is 4 millimeters in diameter and around 1.2 centimeters long. We first wrap it in a layer of aluminum foil to stop diffusion of CO2 out of the core. We then put it in a Viton sleeve and snugly fit steel end fittings with PEEK tubing attached and a thermocouple with an additional layer of adhesive aluminum foil. This is then placed inside a carbon fiber Hassler cell and mounted to the rotation stage inside our Zeiss XRM 500 micro CT scanner. We move the source as close as possible to the core holder in order to minimize noise and take the sharpest possible images. We decided on an X-ray tomography because it is both non-invasive and provides high-resolution three-dimensional images. Our experimental setup is as follows. CO2 is loaded into the front pressure pump and pressurized. This CO2 is then equilibrated with brine in the reactor at high temperature and pressure. The core is confined at higher pressure than the reactor in order to control the exterior boundary conditions of the core. A thermocouple is inserted into a radial port of the cell, is paired with flexible heating tape in order to keep the cell at reactor temperature. Fluid is then pulled through the core for a set amount of time. The carbon fiber sleeve of the cell and flexible tubing allow for images to be taken while dissolution is happening. This is our micro-CT setup, and you can see the flexible tubing and carbon fiber sleeve covered in heating tape that allows us to take tomographies in situ. This micro-CT has an acquisition time of between 15 minutes and 1 hour depending on your required resolution. The stage spins as X-rays are fired through the core, and the difference in attenuation is recorded by the detector assembly. These single projections are combined into a sinogram, and then an algorithm reconstructs them in 3 dimensions. The images are then post-processed. This is the raw image of a 4 mm core of Qatar carbonate at a 3.8 micron resolution. Qatar is a calcite oolite that is relatively homogeneous. We can see that the raw image is rather noisy, however. So to clean it up, we first use a filtering algorithm called non-local means. Non-local means is a relatively new and powerful filter that increases signal to noise while keeping edges sharp. We then binarize the image into rock and void using a watershed segmentation that detects edges using grayscale gradients and grows them from a user-determined seed. When doing dynamic imaging, it is extremely important to use the same segmentation values with all images from the experiment in order to avoid segmentation bias within the time series. Once we have binarized the image, we can create a three-dimensional model of each time step and use them in a variety of ways. Here we see the dissolution through time visualized for each of the 10 time steps. A first-order analysis of the 4D dataset gives us porosity values. On the left, we see the porosity, and on the right, we see the porosity change as a function of distance from the inlet and time. We can see that apart from minor perturbations in the change in porosity due to grain stacking, dissolution is relatively uniform along the length of the core. In a second-order analysis, we could run the binarized 3D images through a Navier-Stokes solver that computes permeability and velocity field distributions by applying a constant pressure drop to simulate flow. Here we see that the velocity fields are relatively uniform to begin with, and the flow paths become wider and less tortuous as dissolution continues, but still have a uniform distribution. This is corroborated by the PDFs of velocity, where we see a narrowing of the velocity distribution. When we plot permeability against porosity, we see that it follows a parallel distribution. Additionally, we see that the effective reaction rate is 16 times lower than the bulk measured rates, indicating that local flow heterogeneities impede mixing and reaction. To conclude, we have established a new experimental method that demonstrates the controls on dissolution and quantifies effects of local flow speed, porosity, and permeability on local reaction rates. This paper is now published and freely available in the online journal Environmental Science and Technology. Furthermore, the datasets are available for download on the EST website in this paper's supporting information or the website of the British Geological Survey, and any code used for image processing is available on GitHub. I'd like to thank our sponsors and acknowledge our references and give special thanks to Martin Blunt and Branko Bijeljic, my supervisors, Matthew Ender for experimental expertise and advice, and Drs. Ali Rahini and Joe Piera Nunes for helping up setting up the Navier-Stokes simulations. If you have any questions, please don't hesitate to contact me, either by commenting on this video or emailing me on my website, hannahmenke.com, or contacting me on LinkedIn. Thank you very much for listening.